Space appears overwhelmingly dark, but the void is filled with an invisible courier. Light carries information across billions of light years, yet remains entirely undetectable while in transit. It travels at an absolute maximum velocity of 300,000 kilometers per second, and unlike ocean waves or sound, it requires absolutely no medium, no water, no air, to cross the empty vacuum. We only realize it is there when it finally crashes into matter. A beam passes through the darkness unseen until it happens to strike a cluster of gases or a piece of dust, reflecting physical information off that object and into our eyes. Everything we know about the structure of atoms, stars, and galaxies comes from intercepting these messages. To understand how the universe operates, we have to look closely at what this invisible courier actually is. For centuries, the forces of electricity and magnetism were treated as completely separate phenomena. Electricity was understood as isolated sparks or the steady push of power from the stacked disks of an early battery. Electricity is the movement of charged particles, like electrons, flowing from one point to another. In 1820, Danish physicist Hans Christian Ørsted placed a simple compass near a live wire. When the current flowed, the compass needle deflected away from the Earth's magnetic north. That tiny physical movement proved that moving electrical charges generate magnetic fields. That discovery led Michael Faraday to ask the inverse question: if moving electricity produces magnetism, could a moving magnet produce electricity? After years of experiments, Faraday moved a magnet back and forth inside a coil of wire and watched a meter jump. The changing magnetic direction physically pushed the electrons in the wire, creating a current. These two forces are permanently linked together. A moving charge creates a magnetic field, and a changing magnetic field forces a charge to move. To see what happens when a charge vibrates rather than moving in a straight line, we must scale down to the atomic level mapped by physicist Niels Bohr. Inside an atom, electrons orbit the nucleus at fixed energy levels. When absorbing outside energy, an electron is forced to jump outward to a higher, less stable orbit. Seeking its lowest energy state, it drops back down, a violent acceleration that ejects a packet of energy. That momentary quantum drop is the exact trigger point. Because of this, the accelerating charge has birthed an electromagnetic wave. The mathematician James Clerk Maxwell took Faraday's physical rules and translated them into the equations that explain how that wave survives outside the atom. As the electron vibrates rapidly, its upward movement creates a magnetic field spinning in one direction and downward in the opposite direction. A changing magnetic field induces an electric field, and vice versa, so these two forces interlock at perfect right angles. They leapfrog endlessly. One field collapses and births the next, pushing each other forward without needing physical matter or a medium to carry them along. When Maxwell calculated the speed of this self-sustaining chain reaction, the math produced a constant velocity, 300,000 kilometers per second. That number exactly matched the known speed of light. The invisible messenger was finally identified. Light is an electromagnetic wave, functioning as a perpetual engine. The wave travels undisturbed until it collides with an object. How that object reacts depends entirely on the wave's frequency, which is set by how violently the initial charge was vibrating. If the vibration is slight, it produces massive, slow waves. These are radio waves. Their low energy allows them to pass safely right through human tissue, making them perfect for global communication. Increase the vibration slightly and you get microwaves and infrared radiation. When these hit matter, their specific frequencies cause water and carbon dioxide molecules to rotate and rub together, generating physical friction and heat. Squeeze the wavelength even tighter, and we reach the narrow band emitted by the trillion-degree cauldron of plasma on the sun. These specific frequencies bounce off physical surfaces and enter our eyes, giving us the perception of color and visible light. But when these waves are born from extreme cosmic violence, like dying stars collapsing into black holes, the frequency skyrockets, and the wavelength shrinks down to microscopic sizes. At these speeds, the wave becomes a physical hazard. Ultraviolet radiation carries enough kinetic energy to strike organic molecules and shatter the structural bonds of our DNA. At the absolute extreme are gamma rays. Their vibration is so concentrated and energetic that when they hit an atom, they tear tightly bound electrons completely out of their orbits, ionizing and destroying matter instantly. From warming a cup of water, to revealing the color red, to ripping biological tissue apart, the wave is exactly the same mechanism, only the speed of the vibration changes the outcome. Earth sits directly in the crosshairs of this cosmic engine, constantly bombarded by the full lethal spectrum of high-frequency radiation. This satellite map shows the concentrations of ozone gas high above the Earth's surface. That layer acts as a critical shield, absorbing lethal UV radiation by breaking apart its own molecules to dissipate the energy before it reaches the ground. Humanity eventually moved from simply observing these waves to replicating the physical mechanisms that create them. By splitting heavy atomic nuclei through fission, we trigger the same high-energy acceleration found in deep space, artificially generating the most destructive wavelengths in existence. Earth's atmosphere protects us from the radiation of distant stars, yet it cannot shield us from our own ability to replicate the universe's most violent forces.